Göktürk is visiting us from Istanbul, from the research lab of AirTies Wireless Networks. Dr. Göktürk is actually a graduate of our department, and he continued his graduate studies in Drexel University. After his master's, he moved on to Sabancı University, got his PhD there, in the meantime visited NYU, and he's at present the Director of Research Engineering at AirTies. His research interests include cross-layer optimization of wireless networks, scheduling algorithms, cross-layer designs, algorithms for Wi-Fi network optimization, in particular mesh network optimization, which are very interesting to me personally, and I am really impressed by the original research that they're making, and the way they are able to put this original research into their products. So I'm very happy that he's visiting us today. And if you have questions throughout the seminar afterwards, feel free to ask, and we will have we will be continuing our discussion after the seminar too, in the tea room. So please join me in welcoming Dr. Sarper Göktürk.
First of all, thank you for this good introduction, and I'm very happy to be invited for this talk and to meet with my old university and people here. First of all, today I would like to talk about the background of AirTies, what AirTies is doing currently, and what is the prospects for the AirTies technologies in the future. In particular, the cloud-assisted Wi-Fi mesh network optimization. But before going to the details, let me go over my outline today. I will first of all describe what AirTies is doing, and then I will go on with the Wi-Fi challenges that we are trying to solve, and I will go over to current solutions that we currently employ in the field, and the cloud-assisted advanced solutions, in other words, the second generation of these solutions, which will be applied in the near future and currently under proof of concept implementation and development. And as a case study, I will give some results of the cloud-assisted channel selection algorithms and proof of concept implementation that we have done in our lab. And I will wrap up with the conclusion and the outlook. So, a brief history of AirTies. AirTies originally is a Turkish company which was founded in 2004 by two Turkish guys, Metin Taşkın and Bülent Çelebi. They were originally in Silicon Valley, and they returned to Turkey and founded AirTies. In the first years, AirTies was mainly a Turkish company, but then it won some international clients in Denmark and Holland. Then it went through Swisscom, then came the Sky at Sky, the British Sky. Then came the Orange, Spain. And now we are working with US operators. Mainly we are an ISP-based company. We are working for ISPs. So currently we are here, like this. Between 2004 and 10, it's Turkey, then Europe. Now we have reached most of the places in the world. You may see it's Singapore, telecommunication and Sky here. And there are some unannounced wins which are in US and in Europe. Okay, so that's basically the history of AirTies. What AirTies is doing is, mainly AirTies is producing Wi-Fi access points, Wi-Fi routers, modems, and IPTV set-top boxes, and that set-top boxes which work as an access point also. So AirTies is providing a home Wi-Fi solution, home networking solution. We call it a premium home Wi-Fi solution. It includes the video-grade communication and wireless communication. So we are mainly a network company, but it's not the enterprise network, but the home network. Today's topic is the Wi-Fi, and as the director of research engineering in AirTies, my main focus is Wi-Fi. I'm not working on the set-top box department, but set-top boxes are now having Wi-Fi chipsets in it, so they are connected. They are connected to the Wi-Fi network. They are part of the Wi-Fi network, and we are also utilizing the set-top boxes as access points also. So a set-top box is not different than an access point from point of view of our network architecture. So when I say an access point within this talk, you may understand that it can be a set-top box, it can be a router, it can be an access point, or a modem itself, correct? So what is Wi-Fi and what's the concern here? Wi-Fi is a major burden for both the consumers and the operators. Since we are working with the operators mainly, we are not in the retail anymore. We were in Turkey, we were in the retail business, but now we are almost 100% in the operator business. So we sell our products to the operators, internet service providers, ISPs. So from point of view of ourselves, the consumer or customer is the broadcast operator. And what their survey says that over 30% of their calls, of the calls they receive from the consumers are related to Wi-Fi issues. So most of the people, so at least 30% of the people are not happy with their network due to a Wi-Fi issue. So what are these issues? Let's go in detail. So Wi-Fi in home is a real challenge because end user expectation of Wi-Fi is extremely challenging. People do not know about the Wi-Fi. They just want to connect to the network, right? They don't know what's going behind. They just want to reach the modem here. And if they have purchased 100 megabits per second, if they have subscribed for a broadband communication which supports 25 megabits or 50 megabits, even 100 megabits per second, they want to see it in every place in their home, right? Every location in their home. However, that's not possible if you use only one modem at home. In this scenario, for example, if you have a single access point in the network, you will have dead zones in your network. And you would not see the speed that's promised to you in every place. And other problems are that their consumers want easy setup. They don't want to deal with the setup process. They don't want to debug their Wi-Fi issues. They want all of these issues to be solved before they recognize what's going on, right? So they don't want to see any problems. So this is the challenge that we are talking about. Let's go into the details of this challenge. There is inconsistency between the coverage and the speed. If you have a single AP in the network, this is a sample from a real house. You will see that you have a broadband coming to your home. It's 100 megabits per second. And you have a high capability modem with maybe 802.11 AC chipset in it. And what it can deliver is a very high speed, and actual throughput values can be as high as 530 megabits per second if you are close by to the AP. However, this is not the case, right? you are in the dining room or another room in the home, and you may see different levels of throughput throughout your house. And even in some rooms, you may not get any coverage. So it is the coverage and speed are actually not consistent, but not only the consistency is not because of the antenna strength or transmit power. As you go to the higher standards like 802.11 AC, in order to achieve this kind of throughput, they are using higher modulation schemes and more squeezed constellations. And to reduce the to reduce the error rates, they have to handle those high modulation schemes. You have to be close by. They cannot transmit at high transmit power levels with those MCS modulation and coding schemes. So actually, as the standards improve, this improves only for close by clients, not for the farther away clients. Because if you are a client, if you are using your tablet here, for example, you are farther away from the access point, you have a huge path loss, and the signal degrades very much, then this AP has to use a lower modulation scheme with a more sparse constellation like BPSK or QPSK, and you cannot achieve high throughputs with those constellations, with those modulation and coding schemes. So you cannot achieve much. And this brings us here. Since those devices which are in the far corner of the home are using lower modulation schemes, they are clogging the network with slow transmissions, because the QPSK transmission takes a longer time than a 64 km or 256 km transmission, if they are using the same payload size and the packet size and the aggregation size. So they are clogging the network. And if you have this kind of tablet which streams, for example, video of 10 megabits per second throughput, then the entire network's capacity drops significantly. As you can see here, again you have no coverage here, and the other one, which was originally 531, around 500 megabits per second, it drops to 150. This is because the other client clogs the network with its own slow transmission. Alright? So we have to avoid this kind of scenarios. The other problem is the congestion and interference. Most of us are living in multi-dwelling units or apartments. So we have neighbors. Neighbors are also using access point, and they are also using the same medium, right? They are using similar channels or overlapping channels. So they are all sharing the same wireless capacity, the airtime. And you are sharing the same capacity with your neighbor. So you have to avoid being in the same channel with the neighbor or overlapping channels with the neighbor. So you have to somehow understand or infer your awareness about the neighbors. So what are AirTies' solutions about this? For Wi-Fi capacity improvement, we have the hybrid mesh network. Hybrid mesh network is a mesh network of access points which can have multiple interfaces, in other words, media for communication with the other access point. For example, an access point may have a power line communication, in other words, a PLC interface, or Ethernet interface, or multiple Wi-Fi interfaces like 2.4 gigahertz interface and 5 gigahertz interface, multiple radios. And also, currently we are working on MoCA, multiplexing over coaxial, which is widely deployed in the US. That's why get some attention there. And the other problem about the interference and congestion mitigation, we have dynamic channel selection. I will go over these in detail in the upcoming slides. Then for mobile clients that turn into bad apples, we have the client steering technology, which is currently being used in AirTies products. And for the users which are not IT experts, which covers almost all the users, we have the cloud monitoring and user app that runs in user devices, and cloud monitoring runs in web. You can enter web page. So what is intelligent mesh network? You remember the same scenario that I showed to you before? Instead of having one single access point, we deploy a network of access points. And I said before that even a set-top box may be an access point. And an access point here. So these access points operate in a smart way, and they operate as if they're a single entity. They are doing this in a distributed way, so there is no master node or any node that controls how they behave or route traffic. However, they are in a distributed way, communicate with each other, decide on which path to route the traffic from, the client traffic. They run shortest path algorithms on the fly with every packet, and for every destination node. And as you can see here, if you deploy a mesh network of access point in the same home, you can almost get to the promised broadband speeds. And while doing this, you are not compromising the much the short range capacity. So this is, and we have, let me mention that also, we have patents on this hybrid mesh technology in US and EU. We have patented it. And we have both patents on how to route traffic within this mesh network, in a hybrid mesh network. And also we have patents on how to set up this kind of a network, a hybrid network. So basically what mesh network does is it monitors the ongoing traffic and the link costs with respect to each link, and computes the end-to-end airtime capacity for that route based on the error rate on that link, and then chooses a route for the traffic. And this is, in fact, the route selection is not done by the source or the destination. It is done by every node. So every node tries to reach to the destination from the point of view of itself in the shortest way possible. And this should be done immediately, because the wireless medium is changing very fast. There's interference, there's path loss, and there's small fading and large scale fading, which affects the, and also there's movement in the house. People move, and the clients also move. There is high variance in the network, so you have to adapt to what's going on in the network very fast. You have to select your route very fast without causing too much error. And this is specifically very important from consumer point, because we are in also the set-top boxes and video devices. So in video, you are not allowed to lose any packets. Consumers do not want to see any pixelation on their screen. So this is a really important case. We have to avoid jitter, we have to avoid delay. These are very important parameters for us. And another important thing in the hybrid mesh network is that we may have Wi-Fi links, and also we may have Ethernet links in between. And if in case that there's a fast Ethernet link, we may partition the network into Wi-Fi islands or mesh islands so that we optimize the airtime usage. So we don't share the medium among our mesh network nodes. I forgot to mention one thing which I think is important. I said that these nodes are, for example, in this scenario, this specific A4920 access point has two radios, 2.4 gigahertz radio and a 5 gigahertz radio. So it's a dual band concurrent device. And the mesh network, the Wi-Fi mesh network, is set up on the 5 gigahertz band. Because in the 5 gigahertz band you have more bandwidth and you can have 8 megahertz bandwidth of transmission. And 2.4 gigahertz band is only for used for the client connection. So 5 gigahertz is used for client and mesh backbone, but 2.4 is only used for the clients. So since these have only one band for mesh links, we have to keep them connected all the time in the same channel, the same mesh network. No, there was an animation. This is what I mentioned here. In case we have the we separate the channel, we separate the islands, we separate the mesh network into islands which operate in different channels. These networks cannot talk to each other except for the Ethernet link that they have. So I mentioned the mesh network solution. Now we have come to the client steering feature.
I have a question. When the two mesh networks are being formed, is the awareness of this Ethernet link taken into account automatically, or?
Automatically, when you connect the Ethernet port, it goes directly to the driver, and it detects the Ethernet link, and also it detects the physical rate speed, physical rate that can be attained on that Ethernet link.
So it goes into the distributed route computation.
Yes.
The presence of this Ethernet link.
Yes. The thing is, I will go to that in detail in the cloud-assisted version of this, because this is currently the current implementation only covers this without the channel separation. However, once we have the cloud assisted version of this, we will be able to see the long-term behavior of the long-term route alternatives that can be used in this network, and the channel's busyness, how idle the airtime is in each channel. Then we will be able to recommend the channel and the connection partition to the network. And once the Ethernet is connected, the network becomes aware of the Ethernet connection here, then goes to the state which was recommended by the cloud. However, without cloud, it's not computationally effective for the APs to periodically look to the network, search for alternative partitions, and carry out that partition once the Ethernet is connected. So this is from point of view of processing, it's consuming, but also from point of view of the storage that we use within the APs also not worth doing this kind of thing, because you have to, for this kind of partition, you have to evaluate multiple kinds of partition alternatives.
But typically the network size is not that large in a whole.
Yeah, yes. Typically not, but in some cases we have to cover more than 6 or 8.
Even that is computation.
Yes. For example, Sky wants us to support 16 nodes in the network, because once you say nodes, it's not only the access points that you put in your home, but that's also the set-top boxes that you deploy. So if you have TV in all of your rooms, it makes maybe 3 or 4 access point capable devices in your network. So they are connected to the network not as a client, but also a access point that can give service to the other clients.
Right.
So that increases the number of access points in the network, not the separate access point that you put in your home. So actually there was a home that was reported to us from Britain, which had, I'm not exaggerating, it's like 19 access points at home, or like that. So they want us to support at least 16. So it is. In Turkey, it's not that big.
But that could change. I mean, people are
yes.
interested in.
Yeah, once you go into every device, if you want to turn every device to an access point also, then it increases the number of access points at home increases. The other thing that I want to show is the client steering feature that we have. The client steering feature enables the network to force the client to connect to the best access point possible from point of view of the network. This is actually a very crucial point, and it's not very emphasized by most of the network operators because this kind of mesh networking was not very available before. Once you introduce multiple access points in the network, you have to control the client's connections, because clients connect to the AP from their point of view. They have a myopic view of the network. They want to connect to the AP which provides the highest signal strength. Their algorithms run like this. However, the highest signal strength does not mean that you reach to the endpoint, the root AP, or whatever AP you are looking for, with the shortest available end-to-end throughput. So there is in our mesh network, every AP continuously monitors the clients, every client, and looks for the optimal connection for each AP. While doing this, it considers the 2.4 GHz options and 5 GHz options and all AP options, and try to maximize the throughput that the client would get if it was trying to reach the root AP, which is the modem pair. So it continuously does this computation. If the algorithm decides that the client would be better off if it was connected to another AP, then it starts steering actions on this client. Unfortunately, there are not many protocols or standards on this. There are some standards that that tell you, like 802.11b and 802.11k also helps this, but 11b is the BSS transition request messaging. However, there is no algorithm, and the clients have their own view of the network. They may not obey your decision. So in that case, you have to persuade the client to move to the other AP. So we have devised algorithms that persuades the client and tries to move the client to the better AP by different mechanisms. And we have also 2 separate patents pending in US and in PCT also. Actually, without client steering, you may not get this kind of throughput because the client may end up connecting to the wrong AP. It may be, for example, stuck with this AP and close the network. This is exemplified here. For example, if you have a 3-story house and the client gets connected to this AP in the first floor, and it goes upstairs. However, it stays connected to this AP, right? In that case, it closes the network, the airtime. We force the client to connect to the best AP here in this case. So it is a crucial feature here.
Can I ask a question?
Yes.
So, isn't there a mechanism that the AP, the access points, do refuse the registration attempt of a node?
Yes, it's a part of the it's part of that. But the thing is, before connection, you are not aware of the client. Client gets connected to you, right? The AP. Then AP tries to steer the client to the best alternative AP. The reason is this: the authentication mechanism of Wi-Fi. The client first traditionally said that it's prop request, but most of the clients do not send prop request. They go with the authentication request. They send an authentication request, and you have to respond to that authentication request as soon as possible, within milliseconds. And within that period of time, you do not have enough sufficient time for the other for asking the other access points to accept the authentication from this client. Also, the authentication is a unicast type of packet and initiated by the client. Client requests authentication to an AP, but you cannot tell the client you cannot say to the client, no, don't authenticate with me, go authenticate with this. There is no protocol that says this. First you accept the authentication or deny the authentication, but you cannot say at that point, no, don't go to this. You accept the authentication, then tell him to go to another AP. So, does that answer your question?
Right. So you can deny it for a long time and it's going to connect to some other.
Exactly. Yes. And within our steering mechanism, we do blacklisting. Blacklisting means that we deny. Even we don't deny, we don't respond to the client, so that client is because denial also has some side effects. Not responding to the client does not have such effect, because if a client gets too much denial from an AP, it doesn't initiate authentication anymore for a certain period of time. So it has some side effects. We have discovered those kinds of side effects because we have seen that it's being used, denial has been used as a security breach in Wi-Fi networks. That's why most of the clients, for example, not the denial but the authentication. For iPhone, for example, if it sends a authentication request and connects, then it's de-authenticated by the AP twice in like 4 minutes, then it does not get connected to that AP automatically, like for 30 minutes or like that. So it has some, these are all related to production level things, I guess, because these also change with respect to the client behavior, and I will go into that in the cloud-assisted version of the client stream. Learning the client behavior is also very important. So this is a result that we have obtained in our field trial. We have seen that if we don't use the client steering, for example, here the yellow curve, the client selects a suboptimal or non-optimal AP. However, when we force the client to select the best AP, it gets much higher throughput. However, there are cases that we were not able to force the client. We force, but it does not obey our decision. There may be cases like that. But overall, we improve the throughput dramatically. So the next thing is the dynamic channel selection. Dynamic channel selection aims at finding the best Wi-Fi channel for the entire mesh network. For this, it's Wi-Fi mesh network nodes periodically scans the other channels, not only the operating channel but the alternative channels. And for 5 GHz, you have 23 20 MHz channels. So scanning all of these channels takes time. And once you go to another channel, you stop operating in your channel. So it's a very delicate operation. You don't want to interrupt your traffic in your current channel. We get the channel scores, which is the available airtime in each channel. All mesh nodes collect this information. Then they infer the entire network's. They see the median from the point of view of the entire network, from not only the point of view of the single point. We have also have one patent in US and UK on this, and also we have two separate patent applications pending in US and EU. The last thing about the current solutions is the remote view and network monitoring tool that we have deployed in world. As you can see, these are the points that we have deployed throughout the world. The job of this is to collect data from the firmware, the APs. We put some critical information to the AP, and we say that, okay, you push some of your logs, critical logs, to the cloud, and we use these logs to, for example, for the R&D work, for example. We try to understand what's going on in the network, because we are testing. We have test labs, and we have teams that are testing these devices, but real home scenarios are very different and very beneficial for research and development cycles also. So we collect data from the field. We use this for research purposes, for statistical purposes. We also provide this data to the operators so that they can debug what's going on in the network. And also, they use it for troubleshooting. And we have deployed this with one customer in the US, tier 1 operator. And they have reduced the call rates because we can identify, actually we give this tool to the operator at the end. The operator can understand what's going on in the network, in that specific home, debug the problem, then maybe upgrade the firmware or change the location of the APs, whatever the problem is. So this is a very important tool, and also this goes with the app for iPad app and iOS app for the debugging and setup purposes. So this brings me to the AirTies advanced solutions, which are cloud-assisted versions of the features that I have described. So what's AirTies Cloud Controller? AirTies Cloud Controller's aim is to perceive the environment, what's going on in the network, and take immediate actions or smart actions to maximize the network performance. This cloud control enables remote management of the network. That's very important, in a proactive and dynamic fashion. So you can act before somebody recognizes a problem. Data is collected in different ways, in a periodic fashion and also an event-driven fashion. When there's a problem occurs, you get the events. And by this way, we have statistical analysis available for us, and we have big data for developing our algorithms and policies. The aim here is you get the logs, you get the data to work on, and on that data you can work on, you can create your algorithms and policies. After you determine your policies, for example for the mesh routing or partitioning algorithm, you define your policies and you end up saying that, okay, this policy works everywhere, or this policy works for this AP set or the network. Then you push this result to the AP, the network, and the network gets the new parameters and acts according to the new parameters, so adjusts its operation. So what are the physical layer parameters that can be controlled with this system, which is what is controllable with this perspective? We can control the receive sensitivity of each device, which means that we can play with the carrier sense threshold. So it has effect on the interference received by the AP. You can try to ignore those interference levels. Also, you can change the transmit power levels. You can say that, okay, don't transmit more than 18 dBm, for example. You can say such things. You can control the operating frequency, control channel, both the control channel and the bandwidth. Also, you can adjust the adjacent channel rejection ratio, which is important if you have heavy interference in a nearby channel. And also, you can control the number of spatial streams or the antennas used for transmit and receiver radios. The MAC parameters that can be controlled are the contention window parameters for each QoS queue, like the best effort, voice or video queues. We can enable or disable RTS-CTS exchange, which is especially important in hidden node cases. If we have a hidden interferer here in the network, RTS-CTS should be enabled. We can control the aggregation size with 802.11 AC. We can aggregate 64 packets at once and transmit at once. We can play with the short and long retry counts. With mesh routing rules, we can change the routing rules and the parameters that are used for path cost computation. And we can change the client admission rules. These are the parameters that we can play with. Also, there are parameters that we can monitor. So, these are noise and interference levels, link quality type of parameters like the vector rate, physical rate. I don't want to go into details, but if you have questions, you can interrupt me and ask. We can measure the idle airtime. So currently we are working on the client steering, measurements and channel selection features and trying to upgrade them to cloud-assisted versions. So what is cloud assistance means for client steering, for example? One of the things we can enable or disable depending on the scenario in the network, depending on the scenario. The most important thing is learning client behaviors, because clients are updating every day. You can, for example, you get an iOS upgrade maybe every month or every 2 months, right? And the client behavior changes. The connection request initiated by the clients change. Roaming capabilities change. Disconnect durations change. So if you have cloud, you have long set of data which you can work on. So you can learn the client behaviors and the client capabilities also. The protocols that are supported by the clients. Okay, APs know this information. However, an information learned by one AP can be used by another AP which has not seen that client before. So we can push this kind of capability information before that AP is introduced to that client. So this will be a proactive type of solution. For the mesh islands, we mentioned a bit about that. For partitioning the network, we are evaluating the using end-to-end capacity of the network for partitioning algorithm. While saying end-to-end capacity, I mean we select a root node. There may be different algorithms that can be used. The good thing about the cloud-assisted versions of this type of features is that you can employ any algorithm that you want, and you can push the parameters to the APs. So you can change the algorithm on the fly. You don't have to upgrade the firmware for that. In one home, you can select the best partitioning with respect to the root AP. You can select an algorithm that optimizes or maximizes the throughput for each client while going to the root AP or the modem. In one other home, there may be a video recorder or a set-top boxes which plays video from another source, not the root AP. then you can optimize the partitioning for that network with another algorithm. So the cloud managed type of network enables and facilitates this kinds of solution. That's why this is very good. This is very handy, and there is too much work that can be done with this kind of architecture. We can measure the interference pattern. We can use the traffic pattern, manage and monitor the traffic pattern, and we can take into account all these patterns and client capabilities into account while partitioning the network. We may not want to partition a network and disconnect some clients which cannot connect to the partition network because the partition network goes to a channel that is not supported by the client. However, if we are aware of the client capability while we are partitioning the network, for example, if the client does not support channel 161, we may say that, okay, this partition should not be in channels 161 because this client is residing in that vicinity, and we would like that client to be a part of that partition. So, this is the channel selection, cloud-assisted channel selection. Actually, this is the we have developed this, and we have proof of concept, and I will show some results on this. Channel selection is one of the most important things that can make use of the cloud, because, as I said before, we do not want the APs to periodically go and scan the channels, because we have only one band that supports the mesh backbone. If you go to another channel, then you interrupt your traffic in that channel. So you have to have small amounts of off-channel scans, and you should go back to your original scan. It means that practically we can go for 20 milliseconds in another channel, and in this algorithm we stay in our channel for 2 seconds, and we go to another channel with 20 milliseconds, and we periodically go for and go back to our channel and scan results. However, if you have this kind of small samples, it does not really represent what's going on that channel, because you go and only measure for 20 milliseconds. There may be a sudden interference at that moment, or there may be no traffic at that moment. You may end up with no traffic at that moment. So you have to have a long range of measurements on that channel, which may be hours or days, or in this scenario we have 7 days of data to work on. So we have small amounts of samples. We can detect the outliers. We can detect what the big picture of the network, and analyze the results. This is clear channel assessment, the idle time amount of idle time in the network. Also, we can analyze the occurrence of radar in that channel. The radar, I'm not sure if you are familiar with that, but in 5 gigahertz, the 5 gigahertz covers starting from 5,150 megahertz to the up to 5,850 megahertz, and it includes the radar channels, which means that there may be a radar in that channel, police radar or airport radars. In case of radar, according to regulations, you have to vacate or empty that channel as soon as possible. You cannot stay if you detect a radar, and you have to detect the radar. There is a requirement, regulation for that. So radar is an important issue in 5 gigahertz. If you detect radar, you have to empty that channel. So you have to detect the radar. If you have such a tool and you see that in one channel you constantly see a radar, for example, once a day you see radar, or you may have a false radar detection, right, in one channel due to your radar. If you detect such kind of a pattern, you may avoid that channel, right? However, this depends on recognition of that kind of a pattern, right? If you have a small sample of that channel, you may not recognize this. So the other things are the client capabilities and the here, the client capability. The other important thing is multi-home concurrent channel selection. Okay, for one network, you can select the channel from point of view of the network. However, if you are working with a broadband operator, ISP, that ISP may control multiple nodes in the same apartment building, right? And you may get data from your neighbors also. And if you put one network in channel 100, you may say that, okay, the neighbor should go to another channel because they shouldn't be in the same channel. We can see and match all these networks in the cloud and see that we may optimize the channel taking into account different networks also. So in our case study, I want to wrap up with this case study. This is the cloud-assisted channel selection, which is developed by AirTies. This is also pending patent in the US. Actually, there are multiple patents pending in the US for this case, the cloud-assisted channel selection. I hope you will get patents on these. In this implementation, we have APs that periodically scan each channel in both 2.4 GHz and 5 GHz. As I said before, they go to the other channel, other than the operating channel, for 20 milliseconds. They collect data, go back to their channel, service their clients, and push this data periodically. Every 10 minutes, they accumulate data, and every 10 minutes, they push this data to cloud. And there is the data is the actually amount of available airtime during that measurement. It's a number between 0 and 255, but you can consider it as a percentage of idle time in the network. Then in the cloud, there are prediction algorithms running to forecast the state of each channel in the upcoming hour, in the upcoming 2 hours, in the upcoming day. So we can play with that. And there are multiple predictions algorithms running, and the output of those prediction algorithms are then compared. Actually, since we have previous data, you run your algorithm and train your algorithm with the previous data, and you test the success rate of your algorithm. Then you have a forecast for each channel. Then for the network, our algorithm selects a channel for the entire network, for the mesh network, and for each AP also selects a 2.4 GHz channel. After this selection, these are named as channel recommendations. These ranked channels are fed back to the mesh network. It says that, okay, from point of view of cloud, channel 100 is the best one. Channel 132 is the second. Use this channel list if you want to switch your channel. And there is a mechanism running in the APs. It can be both proactive and reactive. In the proactive case, the AP moves to the channel recommended by the cloud whenever it gets a recommendation. It selects the best channel. In the reactive case, it doesn't go to the best channel, or it may be operating actually in the best channel. However, it sees a sudden interference in the network. There occurs a sudden packet error in the network. Then in that case, it uses that recommendation to select the channel. This is good because if in that case the AP searches for an idle channel, in the case of the problem, it may end up with a suboptimal channel, right? However, cloud monitors the network for a long time, so it can say that, okay, this channel may seem bad this time, but it is the best channel that you can get throughout the day. And the other good thing is that you can analyze the traffic patterns. Think of it this way. Your network in your home, during the day you are not at home, but at night you come home and you watch video, right? And in that case you have interference. However, during the day you don't have any interference. If you only take into account the information that you gathered within the day, then that would be misleading, right? Your neighbor is not at home. You see that, okay, channel 36 is empty. However, at night it's not empty. It's the mostly used channel. So you can see this kind of patterns in the cloud data. So you can avoid selecting the wrong channel. So this shows the channel recommendation performance that we have obtained in a test environment with 3 APs. And it shows in the x-axis you see the decision period in minutes. It means that what happens, what is the success ratio? The success ratio is defined like this. You select the channel, you select the selection algorithm selects a channel and checks if it is the best channel, actually the best channel. So for the next 1 hour, we forecast the channel to be the best one, but we have the data also. Then we test our forecast against the real data and see if it is really the best channel or not. And we change the decision period. We get data every 1 minute. And if we have the decision period for our forecasting method, if the decision period is only 10 minutes, then our success ratio is not that good. For 5 girls it's 65%, and for 2.4 it's 80%. However, once we reach 30 minutes decision period with this phone, we can reach, for 5 girls, reach more than 95% success rates. So it shows that we can predict the best channel with some certainty, right? And this is actually what our forecast looks like. As you can see in the x-axis, this is the time in hours. It means 220 hours means almost 10 days of data is here, and it's data is accumulated to 1 hour. For example, actually we have data for every minute for each channel. This shows the data for one channel. It's channel 161. The black curve shows the forecast data, and the blue one is the actual data. As you can see, actual data moves a lot, and we are not perfect, but we can keep up with the actual data. Our forecasts are not that bad.
Excuse me, about this figure, do we kind of see a peak during one peak per day, or are we able to see the periodicity here, the daily periodicity? Or?
We couldn't see periodicity in this specific example. We looked for that, but we believe that we may see some patterns.
Is this accumulated data from multiple homes, or?
No, one home.
One home.
And continuous monitoring.
Yes, continuous monitoring.
It's interesting not to see the day and night.
Yeah, we couldn't see day and night because actually this is in
Whose
our.
home is this?
This is. Yeah. We couldn't see this here because this is actually our. This is
your office.
Within our office. So that's why we have always traffic. Yeah, we were hoping to see this kind of patterns. However, we couldn't. For 2.4 GHz, we couldn't see anything like that.
Does this also include the control channel traffic? Maybe is it because of that?
This may be, yes. This is because this is a control channel included also.
If we did this in our department, we would clearly see a period.
No. We were aiming that, but we couldn't see in our view. But I'm sure we will see that kind of behavior if we have sufficient amount of data. And also this also depends on the channel, which channels are being used, sampling period. So the good thing about this kind of thing is you can always play with data and update your firmware. This is not only a cloud problem, also an AP problem, because AP gets measurements and we rely on the measurements of the AP. But we may not get successful measurements from the AP as well, right? We want to avoid that kind of scenario as much as possible and detect the outliers. And And this is the, actually for this, for 5 gigahertz we see some kind of a pattern, but again this is not, in this part we have this, we have some low idle time and relatively high idle time periods, but it's not very apparent with the naked eye, right? So what are the conclusions? So cloud definitely proves to be a valuable network monitoring tool. You monitor the network. And it facilitates continuous integration for embedded devices because you continuously monitor what's going on. You debug what's going on. You can debug your firmware, you can debug your network, and you can upgrade the firmware when needed. You can update the parameters that are being used by the firmware. Unfortunately, cloud immediate response, getting an immediate response from cloud for time-critical decisions are not possible right now. What I mean is, for example, we cannot control the authentication from cloud, for example. Client asks for authentication, requests authentication. We don't have sufficient time to go back to the cloud and respond back. In the Mac layer, you can do it in the application layer. Application layer is not that time critical as Wi-Fi, Mac layer or Wi-Fi. However, in the link layer, we cannot get to that speed. As I mentioned, cloud-assisted solutions provide intelligence that's beyond the time-limited myopic view of a single network. So it's like a big brother that can control everything. It facilitates big data analysis. Seemingly unrelated data can be used for deducing invaluable network insight. For example, you can measure the packet error rate and infer contention, or you can monitor the contention or back of Windows states of each AP and say that, okay, the back of Windows has been increased in every AP. So there is a high probability of collision in this network. So you can detect that kind of things because currently in CSMA, CA, we are not able to detect the collisions. We only detect the error, but it may be due to interference or noise or a packet real collision, right? And long-term predictions are possible now. Long-term pattern recognition are possible. So I guess this wraps up my talk. If you have any questions, I would like to answer them. Thank you very much.